Hello. Good evening. I'm happy to be here, and I should thank the organizers for giving me this opportunity. The work is done with Professor B.P. Mandal, and it's on the archive. So the idea of PT phase transition is fresh idea. It's not been explored before anywhere. So the it's in that sense it's very interesting. The outlines are, first I will talk about the toy model of non-Hermitian complex scalars to set the stage for what follows. Then I will review the model which I introduced 3 years back. It's SUN QCD in the new quadratic gauge, which I have introduced. The crux of this talk is point 3 and point 4. So first I will show that this model is non-Hermitian gauge theory and it exhibits PT phase transition. In fourth point, I will show that in any consistent PT symmetric theory, there is a C symmetry. And I will show that this model also has this C symmetry and its explicit representation is also constructed. Then I will conclude my talk. So the model of non-Hermitian scalar is given by this equation 1. First two terms are the analytic terms. The important term for this talk is this mass term. The theory is non-Hermitian as this M squared is non-Hermitian. Similar mass metrics we will encounter in our non-abelian gauge model also. But the only difference is that this M1 squared and M2 squared will diagonal entries will be 0 there. Here they are there. The discussion of PT symmetry and PT phase transition is easier in this model when we define a doublet like this. So obviously the P and T will be 2 cross 2 matrices, and parity in R squared suggests that P has to be like this, 1 and minus 1 in the diagonal entries. So after choosing this P, only choice left for T is identity matrix in order for the equation 1 to be in PT invariant. And the eigenvalues of mass matrix are given in equation 7. So we remain in unbroken PT phase as long as these eigenvalues are real. So for mod M1 squared minus M2 squared greater than or equal to 2M mu squared, we are in the region of unbroken PT phase. So when situation reverses, we step into the region of PT broken phase because eigenvalues have turned complex, and PT operated on psi plus psi minus is not equal to now plus or minus psi plus psi minus, where psi plus psi minus are the eigenfunctions of M squared corresponding to these eigenvalues. So as I said, any consistent PT symmetric theory will have some C symmetry. So here also it has C symmetry, which is given by equation 8, where C is just P, 1 and minus 1 in the diagonal entries, and this is taken from reference 1, right? So the theory is CPT invariant in both the PT broken and PT unbroken phases. In PT broken phase, the theory also violates CP but preserves CT symmetry. So this analogous thing we will find in our model also. Conjugation. This one. Sorry?
How does C act on phi?
So C is P, 1 minus 1 in the diagonal entries. This one. C is just P, right?
So C times phi is P complex conjugation?
Yes, P complex conjugation.
And then it's antilinear?
Antilinear. Okay. Now let me review the model which I introduced. It is based on quadratic gauge, mu is equal to fx, where capital A, it describes gluons, small a is a group index, and it runs from, for SUN group 1 to n squared minus 1. So the gauge has certain USPs which are related to field theoretic details, so I will skip them. The important point is this equation 10, it has an effective Lagrangian, which we can get from Fabio-Popo method. So the first Lagrangian is the usual Yang-Mills, second is the gauge fixing term, and the third one is the ghost term. So for the presenter, this last term is the only important term, where these C's and C bars are the ghost terms. And the theme of this talk revolves around this field only. So that d mu C is a covariant derivative. And here in the Lagrangian, these A indices are summed over. Okay. So theory has two phases. One is the deconfined or the normal phase, and the other phase is ghost condensed phase. It has the signatures of the confinement. So the normal phase or the deconfined phase is given by equation 10 itself, and the ghost condensed phase is what I discussed now. If you concentrate on the ghost term, which I described earlier, it has this component also. G, F, A, B, C, C bar A, C, C, mu A, mu B. There are two capital A's, so it's some kind of a mass term for gluons. And it has small index A, small index B. So, and both run from 1 to n squared minus 1. So it is describing some kind of a mass matrix for gluons, right? N cross n squared minus 1 into n squared minus 1 mass matrix, right? And what are the entries of the mass matrix? These coefficients. So the coefficients in the mass matrix, entries in the mass matrix have to be numbers, but these are the fields. So what I do, I need to condense them. So when I condense them, I get a mass matrix as in equation 11. So let me halt a bit here and describe the nitty-gritties of this matrix. Although this A appears twice here on the right-hand side, the matrix is with respect to indices A and indices B. So they are not summed over. So only thing which is summed over is C, which runs from n squared minus 1, C 1 to n squared minus 1. So to obtain the masses of the gluons, I need to diagonalize this matrix, right? So when I diagonal, and the things become interesting when we take all the condensates to be the equal. So when I take all the condensate to be equal, I get this matrix. So it is composed of this structure constants of SUN. So this matrix is very peculiar. No matter what n you choose, it has always n into n minus 1 non-zero eigenvalues and n minus 1 zero eigenvalues, right? And this matrix is purely antisymmetric. So the eigenvalues which occur are purely imaginary and they always occur in conjugate pairs, right? So what it means, the n into n minus 1 off-diagonal gluons, which are gluons not associated with the Cartan subalgebra of SUN, have become massive and the rest have become massless. So when we go below the mass scale of these gluons, we encounter strong interaction is carried only by the abelian gluons, which describes abelian dominance, which is the signature of the quark confinement. The another signature of quark confinement is that now the pole of the off-diagonal propagators is on the imaginary p-squared axis. So according to this reference, which I list at the end, is another signature of the quark confinement. So the ghost condensed phase is also the confined phase of the theory. So what is the Lagrangian in the ghost condensed phase? I just need to diagonalize this mass term. So mass term 3 and 8 gluons, there are two, in SU3 there are two gluons which are massless. So I can name it 3 and 8, which are 0. The rest occur in conjugate pairs. So when I expand this mass term, it gets expanded this way. You can see plus im squared minus im squared plus m2 minus im2 squared, like that. So now I will prove the non-hermiticity of this theory in both the phases. So in the normal phase, Lagrangian is given by equation 10. The gluons must be Hermitian because they are real degrees of freedom. So they are Hermitian. I define the ghost property, hermiticity property like this because operation in principle takes you particle to its antiparticle. So when I take dagger, it turns into an antiparticle and vice versa. So when I take this hermiticity property, the normal phase is not Hermitian because this term is not Hermitian. So, and the effective Lagrangian in ghost condensed phase is also not Hermitian because we have got the imaginary mass term. So the important point is the confined phase in non-hermitic in the confined phase is profound as ghosts do not appear in their phase, and non-hermiticity is only because of this gluons only. So it is more profound in that sense. So now I can restore this hermiticity using this what is called inner automorphism. So inner automorphism is basically exchanging just group indices 1 to 2, 2 to 1 like that for other pairs of gluons. So in the adjoint representation, it's given by this matrix. There are certain ones at certain places. And when I square this matrix, I get 1, right? So what I have shown is that the theory in both the phases is non-Hermitian. So it becomes now interesting to study what is the state of PT symmetry in this theory. So parity for gluons is defined like this. Space component get the minus sign, zero component do not transform. So Lagrangian in the normal phase, 10. If I take the ghost property to be the pseudo-scalars, it is P invariant. Okay, it preserves the parity symmetry, but for let me discuss now the time reversal symmetry for the normal phase only. And since it's anti-linear operation, since some of the SUN generators are also purely imaginary, it's not same for all gluons. I will explain it to using XU3. So as we see, there are two sets of transformation for time reversal. For 1, 3, 4, 6, and 8 gluons, space component acquire minus sign and zero component do not change. And for 2, 5, and 6, it's exactly opposite. So when I define the transformation like this, the Lagrangian or the theory in the normal phase will be invariant under time reversal given that the property of the ghosts are defined in this manner. Again, we see that there are two sets, 1, 3, 4, 6, and 8 acquire this imaginary part. The others do not transform. So what I have shown, under the specified transformation, theory is PT invariant, right? And now theory in the normal phase is PT invariant, which I now show that in the confined phase, this PT symmetry is broken. The important term again is this mass term. All these terms will be PT invariant. So its parity for gluons is defined in equation 21, and it is easy to check that the Lagrangian in the PT condensed phase will preserve this parity symmetry, but the problem comes in the time reversal symmetry because of this purely imaginary mass term. When I expand it and apply it time reversal, you can see that it acquires an extra minus sign. So the PT is broken in this phase. And this PT breaking is because of the purely antisymmetric nature of this structure's constants that we have seen. Again, the important point here is to note that this PT symmetry violation is in condensed phase is profound, as the ghosts are not there and it's free of the convention for the ghosts. So the transition from confined phase to deconfined phase to confined phase is showing the PT phase transition. There is a crucial difference which I will come to later if I have a time. But the main thing I have shown to you that there is a PT phase transition between two real QCD phases, right? Now let me come to the C symmetry. In every PT symmetric non-Hermitian quantum mechanics, there is a C symmetry which is defined to improve the PT inner product, right? Because there are certain norms which are negative when I take just PT inner product. And C symmetry solves this. And every PT symmetric theory, there is some underlying C symmetry which is there. So there must be some C symmetry in this model also, and yes, it is there. The inner automorphism is which was defined earlier, is the C symmetry in this model. So the C symmetry in quantum mechanics has to satisfy these three conditions. It has Hamiltonian must be invariant under that symmetry. Order of the PT and C symmetry in whichever way you apply it should not matter, and C squared has to be 1. Now I will show that the inner automorphism which we define satisfies QFT analog of all these three conditions. So the inner product, inner automorphism, it takes 1 to 2, 2 to 1 as I said, and the Lagrangian contains sum over all the indexes. So the Lagrangian is invariant under this inner automorphism. So first condition, QFT analog of first condition is satisfied by the inner automorphism, right? And PT, and now I'm coming to the second condition. PT is a space-time symmetry, and the inner automorphism is purely defined on the group space. So no matter in what order do you apply it on equation 10 and equation 14, which are normal phase and the confined phase, the results will not change. So in other words, they commute. So second condition is also satisfied. And the third condition is already shown, that square of the inner automorphism is 1. So inner automorphism satisfies all of these conditions for the C symmetry. And so what we can say is that this present model is consistent non-Hermitian pretty symmetric model, at least in the normal phase. And it is showing pretty phase transition. Again, as I said, it's in analogy with scalar model. The theory is CPT invariant, where C is now inner automorphism in both the phases. In broken phase, theory also violates CP, but preserves CT in analogy with the model. So the conclusions are, it is the first example of the gauge theory, non-Hermitian gauge theory, where the pretty phase transition is shown, that it is the transition between two QCD phases. It's not that the parametric regions when I tune, where I tune the parameter and I go from one region to the other. These are two real QCD phases, and transition between these two phases is a pretty phase transition. And C symmetry and its explicit representation is also shown. So the present theory is non-Hermitian, consistent non-Hermitian pretty symmetric theory. Thank you.
There is a question over there.
Yeah, I was wondering if you can have a supersymmetric, analog of all this stuff.
There are some works who treat this. There's a BRST symmetry as in superspace and all, but I have not worked in that.
Okay, any other question? Okay, if not, let's thank the speaker again.